Okay, let's try and find the intervals of increasing, decreasing. Let's practice using the simple steps. Let's try it on the function f at x is equal to x squared minus 3 over x squared minus 4. The first step is to take the derivative, set it equal to 0, and solve. But you can see that there are two functions of x here, and you're dividing those two functions. So it's going to be quotient rule. I like to do quotient rule off to the side. So the top function f is equal to x squared minus 3. And the bottom function g is x squared minus 4. You can see that f prime is 2x and g prime is 2x as well. So for the derivative, f prime at x, you're going to get f prime g, so 2x times x squared minus 4 minus g prime f. So minus 2x times x squared minus 3. And that's all going to be over the bottom squared, so x squared minus 4 squared. We should simplify this. So I'll common factor out the 2x that you can see is in common between the two terms, and that's pretty much it that's in common. We get an x squared minus 4 minus x squared minus 3 left over. That's still all over x squared minus 4 squared. Now, when we're simplifying on the inside of the bracket here, you can see that you get an x squared minus an x squared. So those two are going to cancel out. Then you get a negative 4 minus a negative 3. So that's the same as negative 4 plus 3. So we get negative 1 on the inside. So that's going to give us f prime of x is equal to 2x times negative 1 all over x squared minus 4 squared. Simplify on top, and we get, for the first derivative, negative 2x is equal, or negative 2x over x squared minus 4 squared. Now we have to set it equal to 0 and solve. So if I set this equal to 0, right, you can see that this x squared minus 4 squared, you can send that over to the other side by multiplying, so that's gone. So really, we're only solving negative 2x is equal to 0. And now I can finish off and divide both sides by negative 2, so I get x is equal to 0. That's my critical value. So the second step says to plot the domain on a number line along with the critical values. So we can see the domain from the original function is x can't be negative 2 or positive 2 because of the vertical asymptotes. And then we remember that the critical values are x is equal to 0. So if I plot that on a number line, I'm going to get this, right? Woo! So I cannot be at negative 2, and I can't be at 2. And also, I have a critical value at x is equal to 0. So when I look at that domain along with the x-intercepts, I can see my different sections or my different intervals. So I have a section here, I have a section here, I have a section here, and another one here. So 4 different sections. What would the names of those sections be? Let me just move this down a little bit. So what would those sections be? You can see that this one here is going to be negative infinity to negative 2. So it goes all the way to the left, all the way to negative 2. This one is from negative 2 to 0. So we'll write that like this. This one's from 0 to 2. So like that. And then this one is from 2 to infinity. So there are 4 intervals for determining whether those are increasing or decreasing. And that's what we'll do on the next step. So for the last step, we want to take test values from within each interval and then sub it into the first derivative. And we want to see if the answer to that is going to be positive or negative. That will tell us whether it's increasing or decreasing. Positive means that it's increasing. Negative means that it's decreasing. So test values from within each interval. Within negative infinity and negative 2, I think negative 3 would be a good choice. So let's put negative 3 into f prime. For negative 2 to 0, obviously 1 would be a good choice. Negative 1 would be a good choice here, so let's find f prime at negative 1. And here, let's take f prime at 1. And then for this section, let's take f prime at 3. So what I mean is, we're going to take that number like negative 3 and sub it into here. So here I'll do an example down here. So f prime at negative 3 is clearly going to be equal to negative 2 times negative 3 all over negative 3 squared minus 4 all in brackets squared. So you can find an answer. You could put this whole thing into your calculator and you could get an answer and you could see whether that answer is positive or negative. So if you're a calculator person, you can totally do that. But really, we only care about whether the answer is going to be positive or negative. So you can kind of analyze that or do it by inspection. If you look at the top, negative 2 times negative 3, that's clearly going to be a positive 6. So we care about the fact that it's positive. On the bottom, regardless of all this mess inside the square brackets, we're going to square it, right? Because of this 2 right here. So no matter what, it's going to turn out to be a positive. So we get a positive over a positive, which of course is a positive. So since f prime at negative 3 was a positive, that means, so I'm going to write that up here for myself, it's a positive. That means that it's increasing over that interval. So from negative infinity to negative 2. If you keep on going, so if you put in, say, if you put in negative 1 in this spot, and you put in negative 1 in this spot, you're going to get a positive answer as well. If you put in 1 in here, you're going to get a negative up top, and you're going to get a positive on the bottom still, so you're going to get a negative answer. And if you put in the 3, so negative 2 times 3, that's going to be a negative 6. So a negative answer on the top, and a positive answer still in the bottom, so you're going to get a negative. So in conclusion, let me clear some space here. So basically what you get is you're going to get increasing over the positive intervals. So negative infinity to negative 2 union with negative 2 to 0. And then you're going to get decreasing over 0 to 2 union with 2 to infinity. And there's your answer. That's where it's increasing and decreasing. I do a dance of victory, 'cause now I'm living good. No, I'm not living like I used to be. Now talk about